Okay, great. Yeah, so I'm happy to welcome John Wieting to our first MLFL of the semester. Sorry, there's no pizza this time. I know that's a huge motivation for many people to come, but John's work is great. He's a PhD student, or rather just defended, I guess, so is no longer a student at CMU in the Language and Technology Institute. His supervisors are Graham Newbig and Taylor Berg Kirkpatrick. Next week, he's going to start working at Google Research in Pittsburgh. So his work focuses broadly on text representation learning and applying these representations to solve various NLP tasks. He's also worked a lot on language generation, particularly on paraphrasing and related tasks. I've collaborated with John for a couple of years now on several different projects, and yeah, he does great work. Look forward to hearing the talk.
Okay. Yeah, thanks for having me today. Very happy to give this talk. Mohit and I have been working together off and on for, I guess, 4 years now, although it feels like less. Yeah, so today I'm going to talk about, this kind of goes through my thesis work, you know, like the core thread of what I've been doing since I started my PhD. And we're going to talk about like learning and application of paraphrastic representations for natural language. And this is joint work with Kevin Gimple at TTI Chicago, and then Taylor and Graham, who, well, I guess Taylor is not at CMU anymore, but he's at UCSD and Graham is at CMU. Yeah, so representations for natural language processing, I think, especially in recent years, these have become even a bigger deal now with contextualized models like Elmo and BERT. But in this talk and in this thesis, I generally focused on representations at different granularities of scale. Like in the diagram here, I will talk about like subword representations, and then word representations, of course, we worked on briefly, and then the bulk of my work has been on sentence representations. And that'll be consumed like the most of the talk. So here's just an outline. I'm going to go back in time a little bit and talk about word embeddings and some work I did on word representations, and it kind of sets the tone for how most of these models kind of came into view. It all started with word embeddings. And then I will talk about sentence representations, which is kind of a natural continuation of the work on word embeddings. And then I'm going to get into the multilingual space, talking about simple models, and then something that was just accepted to EMNLP, using like a bilingual generative model, which has some nice advantages over my prior work, although it's a little bit more complicated. And then I'm going to show an application of these kinds of embeddings for neural machine translation, with using them as a reward signal for reinforcement learning. So just getting started. So word embeddings, as everyone probably knows, you basically embed a word and it's like a point in a high dimensional space. And these words kind of naturally, they form a little bit of a hub here where, as you see this dense part of it, there were a lot of words are similar to each other as you spread out. And if you zoom in on like word embeddings trained on like a large corpus, like Love or Word2Vec, what you end up seeing is you end up seeing certain phenomena where antonyms and co-hyponyms are near each other in space. So co-hyponyms are words that share a common parent. So like man and woman, they share a common parent as human, but they're not really synonyms. So they're close in the space, but they're similar words, but they're not paraphrases of each other. Same with like old and young, or those are antonyms, but again, these end up near each other in space because of the training objective, where words with similar contexts end up close to each other, and these words do, in general, share a lot of context in common. So my work initially for the word representations focused on trying to tease apart these co-hyponym and antonym relationships and trying to separate the space So things such as elder and youth are now farther apart in the space. Give the embeddings more of a paraphrasing type quality. And the way we did this initially, again, this was years ago, but the same strategy holds true for today, is that when you want to create like a representation that's really good at paraphrasing, it really helps to have two views of the underlying concept. Initially we used something called the Paraphrase Database, where basically it just took advantage of bilingual data, tried to find a non-English phrase that mapped to two different English phrases. So here we have this German phrase, and it maps both to under control and in check. And then you can assume that these are paraphrases of each other since they match the same German one. This assumption doesn't always hold, but it holds often enough that you can create a useful resource. So Paraphrase Database is just a collection of these English text snippets, although it was extended to multiple languages and things in subsequent years. But this is one way to get multiple views, and there's many other ways which we'll talk about. But once you get these multiple views, this is how you can kind of inject this paraphrasing relationship into these distributional models. So, what does this data look like? It looks like this, where, some things it's not perfect. There are mistakes like bad and villain, it's sometimes they're paraphrases, sometimes they're not. And then there's some errors in the data set, of course, but you get these nice natural paraphrase pairs. And the issue, though, is we're going to try to model on this. All we have is positive examples. We don't have negative examples. And so in 2015, what we did was we borrowed some even earlier work on contrastive learning, where we had this, I think people call it a triplet loss now. But essentially what you do is you just sum over your positive examples, and then you have a distance function for for the positive examples. We want the positive example distance. In this case, it's cosine, so we want the distance is kind of inverted. It's not really a distance, but we want the positive examples to have a higher score than a margin plus the score of some negative examples that we obtain in some way. This contrastive learning is like pretty popular, especially nowadays. It's been into the image. People are doing vision representations using this kind of thing. And it actually is a very valuable loss function to be aware of because it kind of comes up a lot. So it's pretty simple. And essentially we're just trying to, we just mine these negatives and we just try to make our positives outscore negatives by some margin. And we can use this loss on like our PPDB data. And so what we did is like just using 100,000 PPDB words, we compared to other works. So at the bottom of the blues, you have words of Eck and Glove, which are just distributional. And then we had the Hill embeddings, and then we got the retrofitting embeddings, which occurred about 2 months before our paper was out. But using just PPDB data, which was also used by some of the others, with this triplet loss, it makes all the difference. And you get a big gain. And so this data set is on the Simlex data set. It's basically a word paraphrasing data set, as opposed to relatedness and that kind of issues, which plagued earlier word similarity data sets. So it kind of corrects this space. So if you look at Glove versus our embeddings, you have issues where like the word rampant is also very, ends up being like synonymous with something called with greed or racism. These are, rampant modifies these nouns, but they're not synonyms at all. And so that's kind of gets teased out of the representations where you do some learning in this way. So these word embeddings, again, we have these two views, and we can make these embeddings more paraphrastic. And these are useful for a lot of tasks. Again, like there's no real word embedding that was useful, like the best for anything, because different tasks look at different things. These are very useful. These have been found very many uses in the literature for things like dialogue, entailment, adversarial examples, paraphrase detection, and some others. So now we're going to talk about sentence embeddings, and it'll follow a very similar strategy. So can you embed sentences? And so, at the time it was kind of like, it was like, you can, but like, are they gonna be as useful as word representations? And why would we want to do this? So naturally, these things have applications for downstream performance. But one view that we had when we started working on this was we thought of a way of actually studying like compositionality of language. We basically decided that if we were able to model compositionality, i.e. take a sequence of words and distill their meaning into a single vector, how would we know we're successful? And we decided that, well, if just like with word embeddings, similar words are together, then, and their embeddings are close to each other, that's a success. We tried the same thing with sentences. If the sentences are close to each other, then we succeeded in abstracting away things that don't matter and distill their semantics into a vector. So how do we evaluate such things? We found these STS data sets that had been used over the previous few years. Again, like they started in 2012, so we did this a few years later, where people would train models on this data, and then they try to match up their scores for their sentences to line up with the human scores. So here are some examples. So in blue is a positive example, red is a negative. And they're on a 0 to 5 scale. So even though the red one has a lot of lexical overlap, it has a very low score because it's a contradictory. So what we try to do is we don't use the trained data at all. We encode these sentences separately, and then we just take the cosine distance. So we're just relying that our representations have teased apart all these lexical differences into their vectors. So another way to do this, if you want to do a little bit better, is to jointly try to model this distance function. Where each sentence attends on the other one, but that's kind of getting away of our goal of trying to truly study compositionality. And
John, we have a question.
Oh, so, sure.
Subhendu?
Yeah, hi. Can you see me, John?
Yeah, yes, I can.
Oh, and I guess if you can hear me, that's good enough. So my question is, when you're talking about similarity between sentences, so here you have an example of a sentence which describes the exact opposite of what the first sentence does.
Mm-hmm.
Would you expect a sentence like this to have a better score than a sentence that's completely unrelated? Or how does that ordering work?
Yeah, so that's kind of getting into how the data sets were labeled. What ends up happening is like these contradictories or unrelated sentences, they all tend to just be at the very bottom of the scoring pyramid. But I think you can make a case that this should have a score of 0, since they really, since they are totally opposite in meaning. But usually it gets kind of complicated when people label these because they usually rely on Turkers who get kind of like to give a little bit of similarity because they're on the same topic, but they have different meanings, which is not what they're supposed to do. So there's a little bit of a data set issue where I guess if I was doing this personally, I would have to think about it. But yeah, it's a really good question, actually. How to
yes, I was just wondering because the decision that you make here is going to affect the models downstream, right? Because if you say that they're slightly more related because they're on the same topic, you're going to end up capturing more lexical stuff than any of this composition.
But our training is all unsupervised, where we're not really paying attention to the evaluation. We just evaluate at the end.
Oh, I see. Okay.
So it doesn't affect our model, and that's why I've always kind of liked these models where they aren't fine-tuned. So I think this is a problem if you fine-tuned BERT on all this stuff, like what SentenceBERT does, for example, versus a model like this, which is kind of ignorant of these kinds of issues, and you just evaluate. But this definitely comes up. So if you know about the SICK data set, it used to be popular. I don't know if it still is so much, but it was like this little set of captions. And the issue with that data set is that contradictions actually have a relatedness score of 3. And different topics have a score of 1. So what ends up happening is like, it kind of messes things up for like these kinds of models, which naturally it's not really a good data set because this problem is even more like extreme in that case. So I've always kind of liked these STS ones because they're a little bit closer to what I would like to see.
All right, thank you.
But another cool thing about these data sets is that it's hard to fit to any domain since like they cover so many different domains. You have tweets, news, headlines, dictionary definitions, image captions, web form posts, and sometimes you have these things mixed together. So you have a paraphrasing data set where one half is tweets. The tweets are aligned with news articles. So you're trying to like, really kind of, you can't really rely on lexical clues too much here, because a tweet is a very different structure than a news article, and you still want to perform well in the task. And here's just a look. So, now we're going forward in time. So here's like a lot of popular sentence embedding models that exist. So you can average, so BERT, of course, doesn't work very well. And BERT's defense is really designed to be fine-tuned. It's not really a model that gives you good sentence representations out of the box. Its method for being created was different. But then you have things like Infersen from Facebook, Jensen from Microsoft, Google's Universal Sentence Encoder, which you have Sentence BERT. And then Teal, you just have a model that I actually trained up for a demo paper that got rejected. But all I did was I just did an averaging model using like some of the stuff we're talking about in this talk. So you can do much better on these like unsupervised tasks with just simple averaging models. Which have advantage of being very fast and also, having better performance in like this suite of these 25 evaluations. So we're also actually using these now too to create like a reviewer assignment algorithm. It was actually used at ACL and AAAI and MLFL. So like we're trying to like get this into some other kinds of things. And it's like one kind of an open question is, what is the difference between a model that uses BERT and one that doesn't, and a simple model and a very complex model? I'll get into that a little bit more at the end of the talk, but it's also kind of an open question. It's something to think about. So how do we learn these paraphrasing representations? So I've already talked about PPDB as one of our sources of data. The important thing is we need these two views. You can also find existing paraphrase corpora if you're lucky. People translate novels, translate news stories. But in general, it's usually very domain specific and not in a huge volume. There's also back translated paraphrase data, which we'll talk about later for sure. That was something that I spent a lot of GPU hours on. And then there's also just Bitext, which is also two views. You don't have to do the translation. You can just have English and some other data in a different language, and it gives you a nice anchor to do this contrastive loss. Encoders, you can do simple things, which work very well for this problem, better than I had expected. And you can also get deep models to work, and you can also have different modeling paradigms. You can have a discriminative triplet loss, or you can do a fancier generative model, which gives you a lot of other advantages. Just getting into the first thing is PPDB. We'll just start training sentence models based on that. So you used word PPDB before, now we're going to use the phrase PPDB, which is a bunch of text snippets. They look kind of like this. And again, these are extracted through that bilingual pivoting. We use the same loss function. We have these negative examples, positive examples. Everything's the same. The only difference is now we have this G function, which is a composition function. So we take a bunch of word embeddings, and the G function consolidates them into a single vector. So this G function, it could be an LSTM, it could be a deep averaging network, it could be a ComNet. You just simply average the embeddings. And so you can try different Gs and see how they do. And one thing to point out here is how you choose your negative examples is extremely important in training these kinds of models. For the first few papers we wrote on this, we didn't really care. We just took, we knew that finding the nearest neighbor of a batch, so we sampled like 100 examples, and then we found the closest negative to the positive. And so that was like a hard negative. And we did that. But then we realized that like these negatives aren't quite hard enough when we started looking at them. So here's like an example where if you just do M is referred to how many batches you're using. If you just use M equals 1, it's not really that related to the bolded sentence. But then if you use like 40, so now you're looking at about 8,000 sentences because their batches were about 100, and then we looked at both sides. So 100 times 2 times 40. It actually looks a little bit like a paraphrase. It's syntactically similar. It's survive and protect. They're somewhat related. The word trying is in both. So you end up getting much harder negatives, and our performance just kept going up. So on the right, we plot performance, and there's quite a bit of a difference. 2 or 3 points is actually hard to get on this task. And so yeah, so how you choose your negatives matter. And in this case, very, very hard negatives made all the difference. Random negatives really just do poorly. So now getting into our modeling. So our first is our natural case of just averaging the embeddings. You know, we found that this actually outperformed a lot of other architectures. In particular, LSTMs, which were kind of thought would work the best, they actually work kind of at the least here. Projection model, can't quite see because it's covered up. One of these is a DAN, which Mo had wrote about a few, earlier in this same year, which is a similar idea of just averaging, and then you have a deep architecture on top. But basically, these averaging models, including DAN and including our projection and just straight up averaging, all exceed these LSTMs on these tasks. And that was kind of an issue as to why, because they're not able to express word order very well. So we had this open question, like, what is going on here? Is it overfitting? Did we tune our parameters correctly? And the answer turned out to be it was a form of overfitting. It wasn't overfitting on, it was a little bit of a test train mismatch where it was doing well on short sentences, but not so well. The sentences, when the evaluation data is on sentences, and that wasn't quite matching up. And we'll talk about that a little bit more in a minute. But the important thing to take away though from this is people may have heard of SIF embeddings or like that came out a year later, and that's kind of, you know, a lot of that's based on reweighting. In our paper, which, you know, at the time we analyzed what was going on here because we're just averaging these embeddings. And the whole point of what was going on was that essentially the norms of the vectors were just being reweighted. So if a word had a lot of discriminative power into deciding the meaning of a sentence, these words tended to be numbers or proper nouns, especially. Their norms greatly increased. But words of very diminished quality, determiners or pronouns, their norms changed a lot much to the worse. And like a lot of this actually is not based on frequency. So, you know, if you do something that's based on TF-IDF, you're going to have issues because you're kind of assuming that the rarer the word, the better. But it's more to do with the tag or kind of like what category the word is in. And that's what this model picked up on. So we couldn't replicate these results just by reweighting with any other, reweighting the norms through any other mechanism. This is learned, and this is crucial to the performance of these simple models. And then, a natural extension of this project was to look at character n-grams. So a big issue, as I mentioned at the bottom of the slide, is that there was this negative correlation between performance and out of vocabulary words. We were just using uncs. So we hadn't had BPE yet. So we were just did an unc, and it had a huge effect on performance. And so to get around these uncs issues is we kind of took a cue from a Microsoft paper about using character n-grams to do search, and they had a deep network and stuff like that, but they use these features. And so we thought, well, why don't we just average these character n-grams? So we just took n-grams instead of just strictly just n-grams of 3, we took n-grams of 3, 4, 5, 6. We averaged them together, we projected them forward, and that was our word embedding. So what this looks like is you just kind of split a phrase up and you just move the window one character at a time. And you keep the spaces and everything. You just add them up, and then you just do like a non-linearity at the end. If this sounds familiar to you, this is exactly what fast text is by Facebook. They did this about a year later, but this is the same idea. But we also did it on words and sentences, but fast text is very popular. But they base this off of this same principle that we were doing. And then I will say that we weren't the first either to do this. In 1992, Henrik Schulze did this as well. So it just kind of shows you that there's a lot of good ideas are, scattered through time, and it's important to be aware of that. But it had a big effect on performance. So these charogram models, on this STS performance, we got 2 whole points just based on using character n-grams. And I guess there's something I haven't really mentioned is the pink bar here. So our goal in these STS tests was we were always chasing the supervised models. So these supervised models had access to the training data, and then they would take the latest thing, and they would take WordNet and BPDB, and then they would train these supervised models. And we were always trying to compete with them just by training in this unsupervised way. So 75th percentile means the top quarter of all systems. So we were able to surpass that. And our ultimate goal was to beat all the systems, which is a hard thing to do, and it took us a little bit more time. For word embedding tasks, the gap is even bigger, which is a little bit surprising since Simlex mostly consists of high frequency words, but another big gap here. And these embeddings, this simple architecture, it has a very strong inductive bias. So if you're trying to do like a hierarchical model, so in Vogue were these hierarchical like NERs or POS taggers, where you take the sequences and you compose them to a word, and then you take a model that sequences of words and then predicts a prediction. Convergence is much faster using these, because of the inductive bias. It's just much faster, and you get similar performance. And they were able to model some things that we didn't quite expect. So if you took a phrase like not capable, and then you went over your word embedding matrix, the nearest neighbors would be like incapable, unable, incapacity. So it's able to sort of have some very weak ability to model like bigrams. But its main power was its ability to handle slang and misspellings. Even words with no character overlap, it could do well, like huge and enormous. So it worked way better than we thought. And it was something to do. Now we have BPE and sentence pieces, which give a nice trade-off between speed and performance. Like if you average character n-grams, you're kind of hitting every single character, which is much slower than just segmenting and then creating representations. So I would recommend that now, but this is an alternative strategy which kind of comes up in certain problems, especially in certain very rich morphological languages, because we did something with entity linking using this, and it was still quite powerful very recently over something like BPE. So it's kind of a trade-off depending on situation. Now I'll talk about like constructing paraphrase corpora, and we had this open question about getting deep models to work. So what we did is we actually found some supervised paraphrase data called SimpWiki, which is basically we have regular Wikipedia, and then we have simple Wikipedia, which was kind of, people would rewrite Wikipedia articles in like kind of the form for a middle school kid or someone who is learning English, and they would kind of just make some simplifications. This is kind of a handy data set. It's not very large, but it's useful for training some of the simplification models as well. But we just used it as a paraphrase corpus, and we just replaced it with PBDB and did our thing. This time we're trying to get these deep recurrent networks to work. So we proposed our own network called a GRAN. Initially we called it a GAN, but then that was kind of taken already, so we switched it. But the GRAN is not important. People still talk about it sometimes, but it was basically like a way to kind of merge a recurrent model with an averaging model, where we have we keep a gate and we look at the context in the back, and then we use the gate times the word embedding, which is xt, and then that will let in some information from the word embedding conditioned on the past. And then we just average these modified gated word embeddings. But the important thing to note about these experiments on this paraphrase corpora was the gap between averaging models and LSTMs. So here, when we go from averaging to models for BPDB to averaging models on this Wikipedia data, controlling for a number of tokens, the performance is modest. It's a small improvement. But for LSTMs, it's quite significant, 5 points. which got us wondering about why this happened for the LSTMs. It turned out then just adding a lot of regularization. We would scramble the sentences up, kind of like how a denoising autoencoder gets scrambled. And we'd add a lot of dropout. And these two things together, we were able to finally equalize the LSTM model with the word averaging model, which is something that we had wanted to do.
John, we have a question.
Oh, sure.
From Raj. Yeah.
Hey, John, can you hear me?
Yeah.
Yeah, just one question. Great presentation, by the way. So for the gated recurrent architecture, it still takes the same time, right? You have to, like, it is recurrent in nature, so it doesn't save us time. We have to have go through each token and like encode them, right?
Yeah, we're not skipping any tokens or anything.
I think so. I guess what you're trying to learn is like make sure like if a word is important in a context, the gate would like be one, and you'll get the important words, and the less important words will automatically be filtered out.
Yeah, we did analysis on this, and it showed very similar to just averaging, where like the gate realized that the same kind of words were important, like proper nouns and that kind of thing. So it would let in more information there, and and then it would, yeah, it was basically like very much related to what it deemed important.
That's very interesting. Did you try like multi-head gates, like a different like copy of parameters as in transformers, but each head would learn to
No, that'd be a cool idea. This was kind of before we thought, people were thought about multi-headed attention. Like a lot of these ideas are old. I'm basically sharing it because it's like a story of.
Yep.
I think there's like a value here in like thinking about things from like an older perspective. But yeah, I think that would be cool to revisit. Is like maybe something here would be nice in the modern framework for certain types of problems.
Yep, I agree. Thank you so much.
But we didn't try that, no.
Yep.
But oh, and then yeah, here's our gram that we were talking about. It's a little bit better, statistically significant. I checked, but not a game breaker or anything. But the important thing is with these deep architectures, and they were at least able, despite having the similar performance, they behave differently. They'd get different things, different kinds of mistakes. So LCMs were much more sensitive to similar syntactic arrangements in the sentences. So they'd kind of do a little bit worse there, but then they'd make it up for it somewhere else by being able to handle multi-word phrases. So with the success of this like paraphrase corpus, what other data sources can we use? So people don't really write paraphrases very much, and these resources like SimWiki, while valuable, they take a lot of effort to make. But people have been translating for millennia, and the data exists everywhere. If you guys aren't familiar with a website called Opus, you should check it out. It has like just like probably 100 gigabytes of parallel data in all sorts of languages, at least a couple hundred languages. So, and this data is created every day, at least for some languages. We have government proceedings. Canada writes everything in French and English. We have news articles. We have company websites. Movies are now in subtitles for, probably at least 30 or 50 languages. So this data is continuously being created. It is a little bit of an issue where it kind of favors certain domains. It's not really a general domain, but it can still be quite useful. So what we did is we took the most diverse and biggest corpus we could find, which is CZang corpus. It's Czech in English. Here are some domains it covered. It's mostly subtitles and legislation, but you also get some interesting things like fiction and medical and tech. And what we did was we created a paraphrase corpus. Essentially, what we did is we call it back translation, which I think creates some confusion because people think of back translation to the English sentence, and then you translate it to Czech, and then you translate it back to English, and then you get a paraphrase. What we did is we took the Czech, and then we just took the state-of-the-art MT system at the time, and then we translated that to English. And so now we get these two English-English pairs, which are called paraphrase pair. And why this works well has nothing to do with the MT system. It's more to do with when people translate, they translate very loosely, especially subtitles. Like Japan, for example, the culture is to really simplify the subtitles. So that they really don't transfer word to word, translate word to word. They really just make a simplification. And it's like just a cultural thing. And people also will translate idioms and that kind of thing. This kind of happens through the human translators that are hired to create this data. So when you do this translation, even if you're just doing literal translations from the Czech to English, you do get good paraphrases just because of how the translators chose to do the translation. So we found that we could get this filtered NMT data. We filtered it just by removing the really obvious issues due to alignment and that kind of thing. And the performance was very similar to the SimWiki, and still much better than PPDB. So this is what we wanted. We were able to automatically do this, and we can do this at scale. Why do we choose this corpus? Again, its diversity is quite a boon. So if you look at these like other popular data sets using MT, Comic Crawl, Europarl News, they tend to be just way too focused on domain. Comic Crawl is web text, Europarl is government proceedings. So diversity is key, not too shocking. And then we look at the quality, there's this natural trade-off here between diversity and paraphrasing. So we have our, these are human rankings where 3 is considered the best paraphrase. And so what happens is you start, these are ordered from an automatic scoring metric. You could think of, I use my old word embeddings. More recent people have discussed using BLERT, which seems to work better. But you basically can create some automatic paraphrasing score, and then as you go up, paraphrasing quality goes up naturally through humans. By diversity also goes down. So this is lower is better. This is like average overlap of trigrams. So you have this kind of sweet spot in the middle where you're getting good paraphrases with a few mistakes, but they're somewhat diverse.
John, we have a question.
Sure.
Joshua, I'll just unmute you. Okay. Yeah, Joshua, do you want to?
Yeah, hi there. So does the paraphrasic quality of these translated pairs depend on the language? Like if you translated, so you gave Czech as an example, if you translated a different language, do you have a sense of like whether some languages are better or worse for this?
Yeah, a little bit. So there are certain trade-offs. So I mentioned Japanese in particular because for a different project, my advisor speaks fluent Japanese, Graham, and he told me that like a lot of the issues I was having was just the Japanese translate just extremely with a lot of freedom. They for subtitles especially. So there you might get better paraphrases because like, they're not trying to be very literal, which would correspond to like, and the Japanese language is so different than English that it's also maybe a little harder for them to be literal because, it follows a very different syntactic structure and different writing system. When you look at something like French, where they can probably translate literally if they want to quite easily due to how close the languages are. But the problem with Japanese, though, is the automatic translators aren't quite as good because there's not as much parallel data either. So you're going to have more artifacts. So I think there's all these things kind of playing into these trade-offs where with some languages, there might be more freedom to do the translation, but then your translation quality might not be as good. But I agree that like it really depends on domain more so than language. But then some languages are going to give you a little bit more of a difference. But whether that difference is helpful for your problem is another thing.
Great, thank you.
We also have one more question, Laurie. Yeah.
Hey, I just have a related question to that. I was sort of curious about how much certain domains will really have an effect in terms of whether it's idiom or if there are other constraints such as meter, or in the case of Disney translations that are huge that have to come down to, you only have so much space and sometimes you just cut out sentences entirely because you only have so much room in the musical line.
Yeah, I would say domain is quite important. So I actually like subtitles. Subtitles are kind of empty a lot, but like you get some really good nuggets. Like I was just talking to before this one of my students, and then she was talking about finding idioms, and I said you should look at subtitles, and I just did a quick rep for one idiom she was talking about, and I saw like 50 or 60 hits in the English side of the data for open subtitles. It just seems so voluminous, and it covers so many different topics because there's so many different kinds of movies. So I'm a big fan of like fiction and subtitles. Europarl tends to be very boring, and they just kind of write about the same thing over and over again. So you don't really get too much richness there, but it's okay to have. But yeah, domain is very important. You can do really well just subtitles by themselves, actually. So if I was just going to do a little project, I would just do subtitles. But yeah. Oh, so what does this look like? So maybe, you know, if you didn't believe me that you can get interesting things, here are some paraphrases, you know, cherry picked slightly, but you can get stuff that's quite diverse actually, if you can filter out in a nice way. So very different structure, different lexical choices. And a lot of this has to do with, you have to give credit to whoever translated, you know, whether they translated Czech to English or the English to Czech. They're able to create these paraphrases by accident. And I think this is something that we can use as NLP researchers. Now we have these STS tests again. So glove is green. Now we have the winning system for each year. So now we're not doing percentiles anymore. We're actually doing the champion system. And it gets a little bit harder towards the end because these systems start using the stuff that we did the year before. So we're kind of competing against ourselves a little bit. But just training on this para-NMT data, we trained about 5 million pairs. We were able to beat every single year with just an averaging model. So the data is just very important, and these simple objectives work well for this kind of task because of the very low, you know, the very strong bias towards a simple model. So now I'm going to move into the multilingual space because we did a lot of translating, and the natural question is, do we really even have to bother with the translating? And it's a good question to answer. But first of all, there's also this notion of cross-lingual similarity. So now you have sentences written. First of all, you can do semantic similarity in any language, right? So we have Arabic, Arabic, Spanish, Spanish at the bottom. So you could just try to find paraphrases in these languages, but you can also want to do cross-lingual. So it's a little bit like finding translations automatically. You might have corpus and you want to find out which Arabic and English sentences are aligned, like which ones are likely translations or at least paraphrases, cross-lingual paraphrases. So you can use Bitext and train the same exact model. And the nice thing about using Bitext instead of para-NMT is that for free you get, if you train on Arabic, English, Bitext, you get an Arabic, Arabic model, you get an English, English model, and then you also get an Arabic, English model. You get all three in one. So now we move to sentence piece here, which is like a type of BPE, essentially. It's a unigram language model, but it's a similar idea. Performance is quite good. They had a task in 2017, and we're able to win for most of these pairs. Spanish English is a little bit of an issue. I don't know what that system did to win so by such a huge amount, but basically using Bitext, you know, you can do this. I will say this though, Bitext has drawbacks. So you might think para-NMT is obsolete, we'll just use Bitext. It's not really true. So issues with using Bitext is that your sentence pieces are often conflate with each other. So you might have the same sentence piece used in both languages, but they're used in different ways. So they get a little bit overloaded, which can kind of hurt performance. The other thing is that you can't filter as well. So a lot of para-NMT revolves around filtering out like boring paraphrases that are almost identical, and also paraphrasing misaligned things. It's a little bit harder to do that when the data is in Bitext. Filtering is a little bit trickier, where it's not quite as clear cut as when the data is of the same language. So, you know, there's a trade-off here, but Bitext alone works just fine. We look at mining Bitext. We compare to Laser from Schwenk from Facebook. We're able to do quite similarly. bigger vocabulary helps a little bit. But binding Bitext is basically all these translations are all scrambled up and you try to put them together. You can measure it through F1. But the difference here is speed. So if you do like, like the Facebook model, like Laser, it's a 5-layer LSTM and it's quite slow. But if you just do this averaging model with sentence pieces, especially, you can do about 850,000 sentences per second versus like 2,600 sentences per second. So if you're doing mining, speed is very important because you're encoding a ton of stuff. So you do it at scale. Now I'm going to talk about our BGT, or bilingual generative transformer. This is something new at UNLP. It's been in review for like a year. It was rejected more than once, but it finally got in. And essentially what this model is basically it's like a different way of looking at this problem. You think of Bitext as a generative process where at first you have some concept that's kind of an interlingua concept that is shared by all languages. It's just a human thing to represent some thought. And then when you make Bitext, you kind of combine that with some English linguistic variable. And that's how you get the English side of this translation pair. And then similarly, if you're doing like French, you can combine that concept with some French variable, and that's how you get the French side. So we call this generative process, where you basically have this semantic variable, which is like the concept, and then these language specific variables, one for both languages. Before to do this, to create a model like this, you have one thing you have to do that's quite different than what we've done before is we actually have to generate now. So we need an encoder decoder architecture where the encoder is making our representation. This is quite different than what we had done before. And one reason why we didn't do this is that this is actually one of the first things we tried when I started working on this problem, is we tried early NMT architectures and they performed extremely poorly. There's a paper by Felix Hill in 2016 where he compares using encoders to simple things like autoencoders. And they just didn't work well at all. And we didn't really know why. It turned out, again, to be kind of an issue of scale, like some other ideas in NLP. At the time, it just was not feasible. But they do actually work. And I studied this problem first, well, if you have a translation system, how can we make the encoders give good sentence embeddings? And so I tried different things. First of all, I worked with BiLSTMs because it gave me a point to compare to, since Laser was a BiLSTM. And what ends up being important is like your encoder makes this sentence vector, and your decoder has to rely exclusively on this vector to do the translation. There's no attention. And so one issue is like, where do you put the sentence vector into the decoder? So what a lot of people were doing was this first row, hidden, where they just initialize the first hidden state of the LSTM and then they keep going. A lot of people, there's lots of papers that do this. Laser, what they did is they used hidden and word. That's at the bottom, where they basically connected it to the word embedding that was being fed in at each step, and then also the initial hidden state. We explored other ways to do it. Like, for example, you could put it, instead of doing attention, you could just attach it where you would do attention. You could put it right before the logit. And we found that basically the higher up in the network it goes, the closer it is to where you start doing the backpropagation, the better the performance, presumably due to cleaner gradients, perhaps, like similar to a ResNet. But yeah, this was actually quite important to get this to work, was to make this observation. The other thing is that naturally you want to have this, get it to work with transformers. So with transformers, some of these things aren't options anymore, but using them in the attention layer and the logit at each layer was enough to get good results. And the other thing is we really want to have a powerful encoder. So we use like a 5-layer encoder and a 1-layer decoder. So our decoder is naturally very weak, which forces the encoder to put in a lot of information into the encoder vector. And the other thing, if you do transformers, is you need to have a big batch size for this to work. And this is something that's observed for other tasks. Translation, batch size is usually important. But for this task, for some reason, it's extremely important. We needed batch sizes of at least 50,000 for it to work. 50,000 tokens, but that's very massive. That's a lot of gradient checkpointing. So that's one other trick to get to work. So again, now that we're able to generate an encoder, decoder, and get good embeddings, we can go back to our BGT. And essentially, this is how the computation graph works. So this is like a VAE type of model, where we start with our observed English and French sentences, and basically we factor we look again. We want to we want to maximize the likelihood of this model marginalizing over these latent variables. But we do the elbow. We then say, well, we can't really do that. So now we optimize a lower bound, elbow, and we introduce these Q distributions. And what we're able to do is we're able to factor this Q distribution into a product of 3 different Q distributions. One for the English encoder, which is an English inference network, one for semantic, and one for French. So now we have 3 encoders, 3 little Qs, but the product of these 3 Qs makes our big Q, which is in this elbow up in the right corner. And essentially what we can do now is we can feed in, for example, our English sentence, we feed into the English encoder, and then we get the mean and covariance matrix for this blue Q. We can do the same thing then through our semantic encoder. We feed in both of them, and then we do some operation, and then we get the mean and covariance of our interlingua semantic inference network. And then we can do the same thing for red. And then having, now we have this full distribution, these full posteriors for all 3 Qs, and we can sample from them. And this is the reparameterization trick that's used for VAEs. You do sampling that you can backprop through. And then on the other end, to compute our losses, then we concatenate them. So to generate X English, we then concatenate, well, the semantic variable with the English variable. And then that will generate the English, and same for French. And then we can be able to backprop through this entire thing to learn all our parameters. And so what happens, like what did all these look like? So again, I have these familiar suspects from earlier in the talk, all these sentence embedding models. Here is our SP. This is just our sentence piece model from before. And here's our translation model. This is our transformer, this is LSTM. So transformer is in purple, LSTM's in orange. And so our sentence piece model is actually still better than our translation models, but our BGT is now actually quite a bit better than our SP model. So we're able to finally beat this averaging model without any weird tricks. So this source separation between language-specific information and semantic information was actually very important to finally beating these averaging models. And to really quantify the performance, since these numbers all kind of blur together, we looked at what we called hard STS. So what we did is we kind of mined all the STS data for all the years, and we tried to find sentences that had like positive labels, but had very little overlap. So that's like hard plus, where there's not a lot of things that these have in common. Similarly, we try to find negative examples where they're almost identical, except they're a little bit different. So these are problems that word averaging will not do well on, because there aren't any, like, there's very little shared lexical overlap. And so like, this is kind of where these generative models do really well, both translation and BGT, because they're able to handle word order at a much better rate than these averaging models, or surprisingly, these models from the literature also aren't able to do this very well, which was a little surprising to me. But the bigger thing is cross-lingual similarity. So now that we're able to do this separation, you'd expect it to do really well at like cross-lingual similarity, like English Arabic, English Turkish, because you're stripping away the language-specific parts of these sentences. So the semantic variable for both languages should be very much the same. And that's kind of like the big difference here. So between like Arabic, Spanish, they're quite similar. But then we get into cross-lingual territory, especially when the languages differ by a lot, like English, Arabic, which are more different than English, Turkish, and English, Spanish. This stripping away helps you do a lot better on this cross-lingual similarity task, which is something we wanted. The other thing is, like, since we're doing source separation, what is happening? Are we actually doing source separation? Like, it looks like we're doing it, but are we really? So we looked at, for example, we did some probing experiments with French. The thing to keep in mind is like the middle column is the semantic encoder, and then the dark green is just our English language specific encoder. So on semantic tasks like STS, subject, object, the semantic encoder does much better at the probing. But for Japanese, it's a different story. If we do Japanese, we find that the English language encoder does better at these probing tasks. And that's just because Japanese and English are so much more different than English and French. So since Japanese and English are so different, the English encoder has to work harder to do more of the lifting here during the generation. And so its performance goes up on these kinds of tasks. Same with syntactic tasks, it's the same story with French. Semantic is doing better. Japanese, it's a different story. And then other things we looked at, such as length, punctuation, gender. So the French language encoder to see if it was doing gender, and we found that it was. So these, follow a similar trend where in both Japanese and French, length and punctuation tend to be more by the English specific encoders. And so, yeah, you can also do some tricks with generation. In a generative model, you can actually generate outputs. So we found that the English encoders were more doing things, with the structure of the sentence. But the semantic encoders usually were encoding the actual meaning or the key phrase. Then I'm going to just briefly talk about neural machine translation and like one application of these kinds of embeddings. So MT, everyone is probably pretty familiar. We just usually train MT systems based on maximum likelihood estimation. We evaluate with BLEU Score, which BLEU is basically two components. You have a brevity penalty, which penalizes you for being too short. And then you have a n-gram precision score, which kind of calculates how many n-grams did you generate that are correct. And that's why the penalty exists, is because you could just generate the and then get like a really high score. So, you have this kind of trade-off between the two. This is an exact match metric, and it's actually discrete. It's not a continuous metric. And when you do reinforcement learning, you end up using a smooth version of this to prevent being zeroed out, called Sentence BLEU, where you basically just add 1 to all the counts. Reinforcement learning is, an old idea. We use something called minimum risk training, which is a little bit different. They both are optimizing the same objective, which is the expected cost. But in minimum risk training, we do some other tricks where we basically sample, we basically re-normalize the probabilities instead of just using the probabilities. And this kind of reduces the variance. They're basically interchangeable. Just minimum risk training has a bigger history in MT. It was something we were able to get to work pretty well. But they're definitely interchangeable. We use our embeddings from this graph here, our good averaging embeddings. And the other important thing is that what makes this possible is these are so fast. Calculating sentence level BLEU in C and running these averaging models and scoring them is only about 10% slower. So you're not really losing any speed. If you try to do Meteor, for example, as a reward function, it would take forever. It takes days and days and days versus like 6 or 8 hours of these models. So if you want to do a reward signal, you need it to be fast unless you're at Google scale resources. So what we did is we used our similarity metric, but we also added a length penalty, just as BLEU with a length penalty. Here, we didn't really have an issue with being overly long or overly short, so we just kind of penalize you for deviating at all from the reference length by a little bit, depending on how much you're deviating. And just a little bit of a study on BLEU is discrete, as I mentioned. If you plot all the BLEU scores from a run of minimum risk training, you get this kind of choppy graph where there's this heavy peak in the middle. We would generate 8 hypotheses, and then if you compare all the scores, all the BLEU scores of all 8 hypotheses with all of each other, you find that 15% of them are actually repeated. So even though their surface forms are different, they have the exact same BLEU score, which isn't providing a very good learning signal. But if you do this distributional reward, the curve is much flatter, and the repetition is only about 1% now. usually in the form of, being like almost exactly the same. So this provides a little bit of more of a signal when you're doing an optimization process. And like BLEU, we all know BLEU isn't great, but this is kind of one of the issues when you train with a BLEU system versus a system trained with reward simile, is that you can kind of see the difference here with like, there's a big difference between like what the simile objective is rewarding versus the BLEU objective. So like in this sentence, for example, in Rome, which is a very important part of the sentence, is completely excluded by the BLEU translation, and it's not really penalized for it very much. In fact, it has a higher BLEU score than the one generated by the simile system. Even though the simile system, gets penalized a lot for rearranging the sentence, it has all the important information, and that's reflected in the simile score on the right. Same with this one. You have a contradiction actually with the BLEU sentence, but the BLEU score is actually still higher for this because this contradiction occurs at the beginning of the sentence, which, BLEU, if you want to make a mistake, you want to make it at the beginning or the end because it'll have less effect on the score. So you start to get these like weird things. Here's another case where the sentences are all paraphrases of each other, but BLEU gives a vastly different score, much higher score to the one at the bottom. So this isn't good for learning because you have very different scores here, but they're really the same thing. So the similar score is a little bit more sane here. It's not really hard to improve upon BLEU as a metric. But we added a length penalty. We affected some STS scores a little bit, but not too much. So how does this do then in real translation? So we're academic lab, so we had to make some trade-offs. We evaluated on the official WMT 2018 test sets, but we only trained on the news corpora, which is much smaller, about 200,000 examples. So our MTs are not state of the art, but we trained using a ComNet architecture from Paraphrastic, and these are higher parameters. And what ends up happening is we evaluated both on BLEU and on our semantic similarity metric. And the surprise here was that our BLEU performance with simile was actually statistically significantly better than when we trained with BLEU itself. So even we did better on an automatic reward that is not really related to the one that we were aiming for. So here it's better for both Czech and German, where the simile risk is outperforming. And then again, for the similarity metric, which is our goal, this is less surprising, but we also outperform. This is also true for Russian and Turkish as well, even more so in the case of Russian. So we were able to actually get gains in BLEU without, using BLEU as a reward. Human evals also reflected this. The human eval scores were higher for all three languages. Turkish, it wasn't, but there was a little bit of a reason for that, having to do with the translator and some other things. But like in general, like it worked pretty reliably. You might say, well, you guys did a ComNet on a tiny amount of data. What happens if you scale up? So this was a short paper I wrote quickly, got into findings. But basically what happens if you do state-of-the-art transformer models, we just used transformer large, trained on all of the German English at WMT, which is about 4 million examples. And we did about 1 million examples of minimum risk training. You can still see the same effects where the WMT test data, the performance for BLEU here is statistically significantly better. It's still close. The bigger gain is on these other data sets, which are out of domain. So you train on WMT and then you evaluate on IT, Open Subtitles, TED Talks. And here the difference over BLEU is much, much greater. We also tried X-simile, which is basically we use a combination of, not only can you compute the similarity with the source, but you can also compute with the reference, but you can also compute the similarity of the source using a cross-lingual similarity metric. And we found that to actually work even better. Well, it's a little unclear how much better it is, but it was, reliably better across all these evaluations. Here's sim again, and here's cross sim. Human evals as well. We had human evals ranked. We took the top 200 different translations and had humans do that for both WMT and the IT, and they also favored this simile objective. So This actually works even in like large scale settings. And then I kind of alluded to this all along. These signals are giving a stronger signal, so for training. And so the convergence is actually much faster. You can converge in like, you know, just a fraction of the time. With BLEU, it needs a lot more iterations. It's a lot more sample inefficient. And again, this is kind of a born out of something I've talked about before, where a lot of these similarity metrics are favoring certain parts of speech over others as they're more important. And so if you look at the accuracy for different categories of words, we find that words that carry a lot more important meaning, just like in the similarity case, proper nouns, numbers, symbols, you know, abbreviations, these are much more accurately displayed in the translations than pronouns and determiners and that kind of thing. We saw that one of the examples with the Rome. So, and again, you know, if you use these other kind of rewards, you get all these gains. You can easier optimization, better performance, and you're more likely to get like semantically richer words correct. I'll talk about future work a little bit real quick. Just some stuff that's ongoing. I think some of you know about some of these projects. So one is, so Mohit and I, we wrote a paper together a couple of years ago where we had, we given these like parse templates and wanted to generate controlled paraphrases that followed these templates. And I'm still very interested in paraphrase generation. So one thing I've been working on with people here, Kalpesh and Mohit, was how can we generate controlled generation, but we have very diverse paraphrases. One question we had is these useful for style transfer, which we have answered. We have a MLP paper, which we're all very happy with. And then there's also the other question of can they be used for augmentation and robustness and this kind of thing. So this diverse paraphrases, what they do is they originally you have data clustered up into these little clusters based on, the type of style that they are, the Bible or tweets or lyrics. These diverse purpose kind of mess everything up, and then you're able to reconstruct them into a desired style. So this was something that we looked at and it's worked. But this is something I'm very still interested in, paraphrase generation. I think it has a lot of applications. And so here there's just some examples. I am also interested in reinforcement learning still. These automatic results from these evaluation metrics are very, I think that they're actually a very good research path forward, because reinforcement learning in NLP has kind of been something that people just assumed is very marginal and not really worth it. And I think if we get better evaluation metrics that better favor what we want from our text, including even using humans in the loop, it'd be very interesting to see what we can do to try and fine tune, we can get so far with statistical methods, and then maybe this is a way to push the boundaries. So I think this is very interesting future work. I also think similarly, I feel like this kind of training setup can also help us maybe be coherent as we generate even longer form texts, like books even. This is more of a moonshot thing, but I think that the way forward through this might be giving some kind of reinforcement during the learning somehow. So in conclusion, I'm sorry I went a little over, actually way over, but the main purpose of this talk was about giving a little bit of a lesson about how to learn these paraphrasing embeddings, what it takes, what you need to do so, the trade-offs between simple and deep models, paraphrase corpora, which have a number of uses, and then applications. So I did, reward for machine translation, but these also can be used for other types of tasks as well. So yeah, and coded models are available on my website for everything talked about here. And so thank you very much. That is the talk.
Oops. Thank you so much, John. This was great. Let's all unmute ourselves and thank John for the wonderful talk. Awesome. Yeah. So We are a bit over time, but I guess we can do one or two quick questions. I guess there were a lot of questions during the talk. So yeah, one or two quick questions. You can raise your hand or yeah. Okay. Joshua?
Hi. So the latent language independent semantic concept that you were talking about, is this like interpretable? Like intuitively, does it like have a meaning in any non-mathematical sense? I'm just trying to square this like philosophically in terms of a semantic concept that's like abstracted from language itself. Sorry, I think that you're muted.
Well, sorry, I don't know how I muted myself. We've probed it and generated from it. It's still a little unclear of what it learned. It's definitely learning some components of the language that are necessary for reconstruction that are not learned by the semantic one. But you know, the probing tasks aren't really, you know, it's only one small. We expect there's something deeper there, but I guess we haven't thought of, you know, really good ways to really get at what they're learning. I don't know. Do you have any ideas? Because this is kind of an open thing.
No ideas.
Okay. Yeah, we just did the simple, obvious things to investigate, but we have some other ideas too. Like we're kind of interested in like hierarchical clustering. Once you do this so we have a multilingual version of this now, of like training like 30 languages, and so we're kind of interested if you can kind of, you know, make a phylogenetic tree that kind of reflects their like relationship with these embeddings. But yeah, it's a little bit of an open thing. That's a good question.
Thanks.
Okay, we can do one more question. Okay, I had one quick question that was about the NMT work. So I was curious to know like why you preferred minimum risk training over reinforce. Like did you try both of them or like?
Yeah, yeah, that's a good question. Initially I tried reinforce, but I didn't get it to work too well. And this was largely, I was relying on a weird code base. What was it called? Oh, Dynet. I was doing it in Dynet, and there were some issues. So I wanted to go to FairSeek, and then I talked to some people at Facebook, and they had like some very ancient code for minimum risk training, and they showed that minimum risk training was better than a whole bunch of other approaches, but they didn't compare to reinforcement learning. So that's how I ended up choosing minimum risk training. And it does have a big history in NLP going back to the statistical era. But practically it was just kind of due to having an implementation I could compare with that I didn't have to worry about screwing up. And, you know, I could just put my metric in and like just verify that it was different and better without having to worry about me favoring. The issue was then when I went to do the transformer experiments, I couldn't use that same code because it was so outdated. I had to take modern FairSeek and then added it in myself. You know, and there were some bugs there to fix out, but you know, again, I could then reproduce my old results, and I was happy with it. So it's more of just what exists, and you know, trying to, as a researcher, not try to change too many variables. But I'd imagine that you could do similarly with reinforcement learning.
Got it. Thanks. Yeah. Okay, let's thank our speaker again.
Yeah, thanks guys for listening.
Yeah, this was a great talk, and I'll just stop the recording.